We live in a world of black box algorithms. We are routinely taught how to operate complex systems, how to input data and get a result, without ever seeing the underlying logic that makes the system work. The subject of arithmetic frequently falls into this exact trap. It often devolves into a series of rote memory tricks, carrying the one, bringing down the zero, mechanics completely disconnected from any physical reality. But over a century ago, a single textbook solved this precise pedagogical problem. First published in 1884, A.P. Kiselev's Arithmetic achieved an astonishing run of success, remaining in print for over 125 years and serving as the definitive mathematical text for generations. More than 80 million children used this specific text to build their foundational understanding of mathematics. The architect behind it, Andrei Petrovich Kiselev, was certainly a mathematician, but his true genius lay in instructional design. The laws of arithmetic have not changed in thousands of years. The content in his book was not novel, yet it stands out as a masterpiece of technical communication. Kiselev's system relies on axiomatic progression. He refuses to teach tricks. Instead, he builds every complex algorithm from bedrock logic, treating the student as an intelligent investigator, capable of understanding why the math works. Kiselev explicitly rejects rote memorization. His governing rule is that absolutely no concept can be introduced before its foundational prerequisites are fully understood. He grounds abstract mathematical laws physically. The student must intuitively grasp the mechanics of an operation in the real world before they are shown a single equation. We can map Kiselev's curriculum as a structural dependency graph, starting from absolute scratch. At the very bottom is the concept of a single object, the unit. Defining a unit establishes the requirement for basic counting. And mastering counting provides the entry point for addition. Higher-level operations remain inaccessible until these lower-level axioms are geometrically proven. This strict sequential progression serves as a blueprint for technical communication in any field, far beyond grade school math. To see how he does it, we will step inside Kiselev's mental model, tracing exactly how he builds the standard algorithms of multiplication and division strictly from first principles. Kiselev starts by defining the concept of a whole number and the act of counting, long before he introduces any standard mathematical notation. He uses simple visual arrays of strokes to prove that a number is, at its core, just a collection of individual units. He introduces our standard decimal system by taking these units and bundling them into tens, and then bundling those tens into hundreds. But then, incredibly early in the text, Kiselev throws a massive pedagogical curveball. He shifts away from base 10 to explore alternative numeration systems, introducing the quinary system, or base 5. The exact same quantity of strokes remains, but bundled differently. He then moves to the duodecimal system, base 12, proving that grouping parameters are completely arbitrary. In section 16, he tasks the reader with converting the base 10 number, 1766, into the base 5 system. Using a successive division algorithm, he isolates remainders to find how many base 5 units fit into 1766, forming the new quinary number 24031. This introduces the concept of hierarchical polynomials. It demonstrates that all numbers, regardless of their base, are just ranks of compound units. By stripping away the familiarity of base 10, Kiselev forces the student to learn pure numerical logic. He abstracts the universal laws of mathematics from the biological quirk of having 10 fingers. With the properties of whole numbers established, Kiselev introduces the next major tier of arithmetic, multiplication. Instead of declaring the commutative law as a rule to be blindly memorized, he proves it geometrically. Reading this array horizontally gives 3 groups of 7. Reading the exact same array vertically gives 7 groups of 3. The product is identical regardless of order. This allows him to introduce the next critical step in his architecture, the distributive law, dictating how to multiply a sum by a single number. Kiselev's rule is exact. To multiply a sum, you must multiply each term separately and then add the results. He applies this foundational law to decode the seemingly arbitrary mechanics of multi-digit column multiplication. This ledger shows multiplying 3,826 by 472. Multiplying by 2 yields the first partial product. Kiselev reinserts the invisible zeros that standard methods omit to explain the leftward shift. The student explicitly multiplies by 70 and 400, mechanically required by the distributive law. The standard multiplication stack functions as a strict logical application of the distributive law across place value ranks. This rigor continues into division. This is typically where modern math instruction completely devolves into rote memory tricks, like the famous bring down the zero. Kiselev completely refuses to use black box tricks. Instead, he frames the process of division entirely through the lens of place value decomposition. This ledger outlines dividing 64,528 by 23. First, distribute the highest rank, 64,000s, into 23 parts, yielding 2,000 each. The 18,000 remainder cannot be distributed evenly. Kiselev explains bringing down. Those 18,000s shatter into the next lower rank, becoming 180 hundreds. Combined with the existing 500s in the dividend, we now have 185 hundreds ready for the next round of distribution. This cascading physical decomposition continues down through the tens and the units ranks. Kiselev makes the student visualize the actual ranks of numbers breaking apart, rather than just moving digits arbitrarily on a page. The long division bracket serves as an elegant ledger designed to track the physical, cascading decomposition of numerical ranks. Zooming out from specific algorithms to view Kiselev's pedagogical design reveals the strictness of his model. Understanding the unit built the logic of base systems and counting. These axioms paved the way for geometric proofs, yielding the distributive law. With a flawless foundation, the highest-tier algorithms derive from inevitable logic. Kiselev's text respects the reader's intelligence by introducing absolutely nothing without a prior structural reason. This methodology extends far beyond a 6th-grade math classroom. Whether you are writing software documentation, explaining quantum physics, or designing a user interface, axiomatic progression is required for true comprehension. Effective technical instruction builds the mental architecture that makes the algorithm inevitable.